Hi, welcome back. So in the last video, we illustrated how we could take our document term matrix representation of our text data and use it to build a powerful machine learning model. Specifically, we illustrated in the last video that you could take our document term frequency matrix and train a single decision tree using 10-fold cross-validation repeated 3 times and produce an estimate of accuracy of more than 94%. So generally speaking, what that means is that if we built a model, a single decision tree model, and put it in production, we would expect it to be able to predict correctly legitimate text messages, that is ham, from illegitimate text messages, that is spam, more than 94% of the time. It should do that correctly more than 94% of the time. And that's pretty good. That shows us that document term frequencies matrices work. And more specifically, it tells us that this bag of words model, that is, taking our free-form textual data and running it through a data pre-processing pipeline consisting of things like stop word removal, tokenization, stemming, so on and so forth, actually works. Right? It's powerful. It works. It allows us to ignore things like context. For example, do we mean running in terms of a human being moving as fast as they can under their own power versus the IT context of a computer program running? We can actually say, look, these things don't matter. We can rely on the bag of words model to differentiate between those two contexts. We also have shown now that word ordering, we can get a lot of power out of this representation without worrying about word ordering. Okay, cool. But here's the thing. As powerful as this representation is, there's still some room for improvement. We have some issues that we can address. So first and foremost, there's this idea that longer documents will tend to have higher term counts. And this is actually a relatively intuitive idea. Let's take the example of 2 documents. And they're in the sports subject area. More specifically, they're about baseball. And let's say one is a baseball article from Sports Illustrated magazine, and let's say it's around 1,000 terms. Or it's 1,000 words, let's say, total. And then we'll have the book Moneyball, which is also about baseball. And let's say, and I don't know for sure, but I'm making this up. So let's say the book Moneyball is 20,000 words. Now they're both about the same subject area, baseball. So we would expect very specific terms related to baseball to occur in both documents. Terms like ballpark and umpire and strike and bunt and RBI, you name it, right? There's a bunch of terms that are specific to baseball that we would expect to co-occur in both the Sports Illustrated baseball article as well as the book Moneyball. Now, intuitively, we will also realize that where those terms occur in both documents, it's far more likely that Moneyball will have higher counts of those terms just because Moneyball is just a longer document. The word umpire is just more likely to show up more frequently in that document, in the Moneyball book, than it is in the Sports Illustrated article. That's just intuitive. So that's one thing that we need to address. That would improve things. The other thing that we need to address is this idea that terms that appear frequently across the corpus aren't as important. So for example, let's say that I have a collection of documents, and once again, we'll just use the example of American baseball. And let's say I have every article about baseball that ever appeared in Sports Illustrated magazine, and that is my corpus. That is the collection of my documents. If my subject area is limited only to baseball, and more specifically, articles from Sports Illustrated magazine about baseball, it's highly likely that certain terms will show up in many of the documents. For example, the word umpire. It may be entirely possible that the word umpire may show up in 70% of the documents, 80% of the documents. Or here's an even better example. It's extremely probable, it's extremely likely that the word baseball itself will show up in 100% of those documents. It's not unreasonable to assume that Sports Illustrated articles about baseball, every single one of them will contain the word baseball, the term baseball. As such, you could make an argument that in that particular case, the term baseball isn't that important. If it shows up in every single document, how important can it be? It's not providing you a lot of information. It's not providing you a lot of information. So that's another thing that we can address. So here's the thing. We can improve upon this bag of words representation. We can improve upon our document term frequency matrices if we can achieve the following. One, if we can normalize documents based on their length. Whether I'm talking about a 1,000-word Sports Illustrated article about baseball, or I'm talking about a 20,000-word book like Moneyball, if I can normalize their term counts across both of those documents, irrespective of length, it puts those two documents on equal footing. And that's a good thing. That's a good thing. Because usually we're not worried about so much about document lengths. We tend to worry more about the words that show up and how frequently and how important they are within the document themselves. So normalizing the documents based on their length will help us with that. Second, if we can penalize terms that occur frequently across the corpus, that will also help us in our representation. That will make it more powerful. Again, for example, if my corpus is every baseball article that ever showed up in Sports Illustrated magazine, and the word baseball shows up in 100% of those documents, if I can penalize that term so that all of a sudden it looks less important, that would also help out. Because the term baseball is not likely to be predictive. If it's in every document, how can it be predictive? By definition, it's not going to be very predictive. So if we can adjust our matrices to accommodate these two things, it'll increase its power. Okay. Enter in term frequency inverse document frequency. This is exactly what TF-IDF addresses. So first up, let's take a look at term frequency and what does it mean. So we're going to get a little bit mathematical in these slides, nothing too serious, so hang with me on this. So if we let a function that we'll call FREQ, or frequency, the function frequency as defined by T and D, and we let that function be the count of the instances of term T in document D. So if we just define a function that says, look, for any term in the document, just count up how many times it shows up. That's basically all this means, right? So for example, if it walks like a duck and it quacks like a duck, it must be a duck. The frequency of the term duck in that document is 3. The word duck shows up 3 times. So further, let's define another function called TF for term frequency. And the TF for T and D would be essentially the proportion of the count of term T in document D. So for example, if I had a particular term that showed up in a document 4 times and the document was 10 words long, or had 10 terms in it after my processing pipeline, after stemming and stop word removal, let's say, then that particular term represents 40% of the document, 0.4. That would be our expected value for that particular term for the term frequency in that document. Pretty simple. Just what's the proportion of the term in the document, right? So we can represent that mathematically using this calculation. So the term frequency of T given D is essentially the frequency of T in D divided by the sum of all of the frequencies of all the T's in the document. This essentially just gives us the percentage, the proportion. So that's pretty simple, right? And notice how this achieves that first goal. This normalizes across documents. It essentially says, look, you know what? I don't care how long your document is. Just tell me what the relative proportion of this particular term is vis-a-vis the entire document. So again, if you take a 1,000-word document that is a article about baseball from Sports Illustrated, and you compare it to the book Moneyball, you can now say the term umpire is on more even footing, because irrespective of which document is longer, you're going to talk about how prevalent is umpire in terms of the proportion of the document in total. So it normalizes. So this is a way to normalize the term frequency across documents of different lengths. Sweet. So the math works out. It helps out our goal. Okay, next up we have inverse document frequency, or IDF. So if we let capital N be the number of documents in our corpus, that is the number of documents in our collection. So for example, if I had 1,000 articles about baseball from Sports Illustrated in my corpus, that was my collection of documents I was working with, capital N would be 1,000. If I define a function called count of t, where count of t just represents the number of documents in which term t appears, this is also relatively intuitive. Let's say, for example, once again, I have 1,000 baseball articles from Sports Illustrated magazine, and let's say that the term I'm interested in is the word baseball, and as we surmised earlier, let's say the term baseball shows up in every single one of those documents, count of t would be 1,000. Baseball shows up in every single document in the corpus. There are 1,000 documents in the corpus, ergo count t is 1,000. Pretty simple. So given that, the IDF is essentially the log of the number of documents in my corpus divided by the specific count of a term. In how many of the documents across the corpus does the term actually show up in? That's all it is. So once again, notice that if I had capital N be 1,000, right, because I had 1,000 Sports Illustrated baseball articles, and then I said, look, I'm looking for the count of the term baseball in my corpus, and assuming that baseball shows up in every single article, I would have count t is also 1,000. So N would be 1,000, count t would be 1,000. 1,000 over 1,000 is 1, and the log of 1 is 0. Notice how this math also works out. Term frequency normalizes, that was our first goal. This one discounts, penalizes terms that show up frequently across the corpus. And in particular, if a term shows up in every single document in the corpus, this mathematical equation essentially gives it a weight of 0. You can't get much more penalized than that. Essentially, it says, look, baseball is useless. If baseball shows up in every single document in your corpus, there's no information in there that you need to worry about. So cool. We now have a mathematical representation of how we can address some issues in our document term frequency matrix representation. Okay, so this leads us to the mighty TF-IDF. So if we combine TF and IDF, we can enhance our document term frequency matrices to make them more powerful. And TF-IDF is very simple. It's simply the TF of a term for a document times the IDF of that term. And we'll see what that means here in a second in actual R code. Okay, so here we are in our R environment, and I've ran the code through essentially the end of video number 4 to set up the environment. So the first thing that we need to do is, if we're going to use the mighty TF-IDF in our solution, and I would suggest that we should try it out, because most of the time, almost all the time, TF-IDF actually helps you out. So it's actually, generally speaking, a de facto part of most text analytics data pre-processing pipelines. You lowercase, you remove stop words, you remove numbers and symbols and hyphens, you stem, and then you run TF-IDF. That's a prototypical data pre-processing pipeline in text analytics. So we're going to go ahead and hand roll our own TF-IDF functions, and we're doing this for 2 reasons. One, it's educational and illustrative of what's going on behind the scenes, and 2, it allows us to calculate our IDF values for all of the terms in our training data, so that we can cache that, we can keep that vector of IDF values and use it later to transform our test data into comparable representations. And that's super important, and we'll talk more about that later, but just to give you a heads up. Okay, so first up, we need to define a function in R for calculating our term frequency. So here's the code that we can use to do that. And notice that it's pretty simple, right? If a row in my document term frequency matrix represents a document, which it does, it's pretty easy. take every member of the row and just divide it by the total of the row, right? R does vectorized processing. So this will essentially say, go through the first column, divide whatever's in that first column, that first cell, the first vector, the first value in the row, and divide it by the total of the row. And this just gives me the percentage across all the individual terms in the document. Nothing too difficult here. So we can just run that code and create our function. Sweet. Now, IDF, inverse document frequency, is a little more complicated, but not astronomically so. First thing we do is we say, okay, look, we do TF on rows, right? We normalize across each individual document, which is our rows. In IDF, we calculate by column, right? Because we want to actually look at the terms now. Term frequency is document centric. IDF, or inverse document frequency, is corpus centric or column centric. So notice how we're working on columns versus rows. So the first thing we need to do is we need to calculate for each one of the columns, how many documents are there? What's the length of the column? Now, generally speaking, this is going to be the same for every column, obviously, because we have a matrix. And then our document count is exactly what you would expect, which is, okay, just give me the number of rows where the column is not 0, right? The count of this particular term for a particular document is more than 0, right? That's what we care about. That's what we care about for this particular term. And how many documents does it appear? That's what this code does. Cool. And then lastly, we take the log. Now notice in the slides, I used log generically and I didn't specify a base. Technically, it doesn't really matter. We'll use base 10 here because that's actually commonly used in implementations. For example, if you want to compare this code that we're going to be using to the quantita TF-IDF function, this code here will generate essentially the same output as quantita does if you make sure that quantita also normalizes, which it doesn't do by default. So if you want to double check this with the quantita TF-IDF function, you can go ahead and do so, set the normalization to true on that, and you will get exactly the same numbers as we'll see this code generates. Okay, so now we've got TF and IDF. So if I run this function, this will generate my IDF function. And then lastly, we combine the two into our own custom TF-IDF. And as we saw from the slide decks, that's pretty easy. I just multiply X by IDF and good to go. Actually, you know what? Let's change this. Let's make this even more specific. Let's make this TF instead of X times IDF. That's better yet. Cool. Look at that. Nice. Okay, so now we have our TF-IDF function. So we have all of our functions that we need to make this work. Okay, so first up, we have to do some matrix transformations. Right? We have this matrix, this train tokens matrix, right, from last time. So if I do a quick view on that, I'll just highlight this real quick and pop that bad boy in here. It'll take a second to pop up in the spreadsheet view. But you can see here, right, this is just all of our terms across the top and all of our documents down the side here and just the individual counts, right? 111, 212, so on and so forth. Great. We need to transform that. First step, obviously, is that we have to transform all the documents using the TF function. We need to normalize all of our documents. We want to get rid of that. We want to address that first issue, which is we want all of our documents, irrespective of length, to be on equal footing. So we need to normalize. So how we do that is we use the apply function. If you're not familiar, you can always pull this up in the help file, and apply functions over array margins, right? This essentially says, look, you can have R automatically apply a function over and over and over again, either against the rows or against the column of the matrix. This is a way that you can loop in R. If you're familiar with programming, this is essentially an R-style for loop. So here's what we can do. We can apply our term frequency function against this matrix, and the one says do it against the rows. So if I run these 2 lines of code here, what's going to happen is that it's going to apply the function against the rows. Now you'll notice something really super interesting here. I ran the dim here so that you're aware of this. Now originally, if I do dim on this matrix, notice that I had 3,901 rows and 5,743 columns. Notice that this is the output of this function call has transposed our matrix. It's essentially swapped the columns for rows. And in linear algebra, that's known as transposition. I've transposed the matrix. Notice I haven't lost any data. It's just basically swapped the rows for the columns. Just be aware of that. So we can quickly take a quick view at this and just see how things have been swapped from last time. Now the rows are now columns, and what used to be columns are now the rows. But notice that the numbers are now different. Notice that these used to be ones, right? This is our first document here. Whoops, excuse me. This would be our first document right here. And notice that these used to be ones, but now they're 0.0625 instead. These have been normalized, right? They've been normalized, which is cool. Okay, so next up, we need to calculate our IDF vector. We need to calculate our IDF vector. And remember I said earlier in the PowerPoint that we're going to want to cache that. We're going to want to store it because we want to transpose, well, not transpose, we want to transform. We want to be able to map any brand new data once we go into production and new documents come in, new text messages come in. We need to be able to transform those new text messages into the same space that our machine learning model was built. So to do that, we need to make sure that we store, we calculate the IDFs and we store them, because that is the fixed set of IDFs that we use to train our machine learning models. Therefore, in our test data, any brand new production data, we need to use those same IDF values to transform new data that the model's never seen before into a space that it understands. Okay, so what we're going to do here is we're going to go ahead and use the apply function again against the matrix. But notice this time we're going to apply the IDF function, the inverse document frequency function, against the data set. And this time instead of the rows, we're going to go against the columns, right? Because that makes sense, because IDF is not a row-based calculation, it's the column-based calculation. So if I run these 2 lines of code real quick, it'll take a second, and you'll notice that I get back a single vector, a single numeric vector that is 5,743 in length, and you'll notice here are the individual IDF calculations that correspond to each one of our terms. Sweet. So now I've got the TF, I've got my documents normalized, and then I also have the IDF values that I use. Okay, so not surprisingly, here we go. So we can apply the function again. Now this is going to get a little more interesting. We're going to apply on our data frame, right? Not our data frame, on our transformed, our normalized matrix here, right? This is our TF normalized matrix. And notice here, because the matrix was transposed, we're going to run against the columns, and we're going to apply the TF-IDF function to it, and we need to pass in our IDF vector values. So now if I run this, take a second, I'll notice that I've still maintained my transposed matrix. Remember, we originally had 3,901 rows and 5,743 columns. We've still maintained this transposition, which is why we oriented to the columns. But if we take a look at the data now, we should see that it's been transformed. Notice that the values now for text 1, they used to all be the same because they were normalized to that individual document vector. Now they're rationalized. They have been combined with the TF and the IDF values to achieve our 2 goals. The goal of 1, normalizing documents based on their length so that we can compare documents on equal footing, and then 2, rationalize individual terms in our corpus to say, look, those terms that appear more frequently are going to be less useful than those terms that appear rarely. So for example, by definition, higher numbers here will represent things that appear less often. So for example, the word go, the term go, it's intuitive to us that it appears quite a bit because you'll see the lower score here. Whereas jurong has quite a bit higher score. And intuitively would say, yeah, that makes sense. I would expect that in English SMS text messages, the word go, the term go, the token go should happen to occur a lot more often, generally speaking, than the term jurong. Okay, cool. So now we've got a mighty TF-IDF matrix. Excellent. So now here's the thing. We need to transpose it back, right? We need to get it back to be a document frequency matrix. Right now, it's actually in a term frequency document matrix format where the term frequencies are the rows and the documents are the columns. That's okay. You'll see most of the literature or a lot of the literature in text analytics actually use that representation. However, when you get ready to train a machine learning model, you'll need to flip it back. So that's what we'll do here. We'll use the T function. And if you run the help on that, the T function is a matrix transpose. So that's exactly what we'll do here. We'll go ahead and transpose our matrix. And notice we get back to our original representation. 3,901 documents with each one having 5,743 columns. And if we just view that real quick in the spreadsheet view, all is right with the world. We've now invoked the mighty TF-IDF on our document term frequency matrix, and we've got all kinds of predictive goodness in it now. Okay. But let's test it out. Let's test it out. Let's make sure that, in fact, I get the goodness that I expect. But we've got a little bit of a problem that we need to deal with here. We've got a little bit of a problem to deal with here. When we invoke TF-IDF on something, we need to actually check for a particular degenerative case. And that is the case of after we've done all of our pre-processing, we've removed all the stop words, we removed all the symbols and numbers and etc., and we've stemmed, it's entirely possible that there's nothing left. There's nothing left. We basically remove everything from the string. So imagine if I just put a bunch of emoticons in a particular text, right? A bunch of smiley faces made with colons and dashes and parentheses and things like that. Those are all symbols. So our pre-processing pipeline would strip those all out. So we could actually have empty strings. Now, when we do a TF-IDF calculation on an empty string, we'll actually get essentially errors from R. So to check that, we can actually say, look, you know what? Go through my new mighty TF-IDF matrix and check out to see if there are any cases that are not complete. So for example, anytime there's an error in the calculations of TF-IDF, I'll get not a number as a result, and that will trip this complete cases function. And this is a way for me to test to see, look, did I in fact have any text messages where essentially I stripped everything out and there's nothing left, so I have essentially an empty string. So we'll go ahead and do that. And you'll see, yep, in fact, I do find cases that are not complete, in fact, incomplete cases. And if I go look at the original text messages of some of those, here's what I get. What are you doing? How are you? Well, we know these are punctuation, so we'll strip those out. And we also know that every one of these is a stop word. So therefore, this particular text gets essentially turned into an empty string from our pre-processing pipeline. In a similar way, this is just numbers, so our pre-processing pipeline will basically strip that all out, making an empty string. That's just a bunch of symbols, so our pre-processing pipeline will strip those all out and make it nothing, and so on and so forth, right? Same thing here, so on and so forth. Okay, so here's what we do. We can fix those incomplete cases up, because if we try to train a machine learning model with incomplete cases, most of the machine learning models that you use in R will throw an error. So we need to fix these up. And that's pretty easy to do. All we do is essentially say, look, for any row in my TF-IDF matrix that is incomplete, just replace it with all zeros. Just replace it with all zeros. It should be fine. We don't want to get rid of those rows because it's entirely possible that text messages that are essentially get turned into nothing by our pre-processing pipeline may actually be predominantly ham, right? Legitimate. These are probably legitimate text messages. These are probably legitimate text messages. Very likely. So we don't want to lose those records. So we just replace them with all zeros. And if there is any signal in the data, what will happen is that our machine learning model will pick up on that and actually show us what's going on. Okay, so next up, now that we've identified that we have some incomplete cases that we need to address, let's go ahead and fix them. So simply what we'll do is we'll just say, look, any place in my IDF that I've got missing data, I'm just going to go ahead and replace that with all zeros for all the reasons that we just described. So if I run on these lines of code, you can see here, I've still maintained my dimensions. Everything's great. I've got 3901 rows and 5743 columns. And notice now that I have no incomplete cases. I've taken those instances of those documents, those text messages where our pre-processing pipeline has essentially stripped all of the data out and made them empty strings. I've now replaced those with 0. So again, if my machine learning model can do it, it will learn some signal. Okay, last up, what we'll do is we'll clean up our data frame names, just like we did before, and get ourselves a nice, clean data frame. Now this time, instead of it just being the raw term frequency counts for each of the documents, it'll be the mighty TF-IDF adjusted scores for each one of those terms in each one of the documents. Okay, so now we're all set up and we're good to go. Since we're close on time now, I'm going to go ahead and stop here. And what I'll ask you to do is please, 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 if you have any questions or comments or concerns, please use the comments section of the video on the Data Science Dojo YouTube channel. We monitor the channel frequently and we try to answer any and all questions and comments and concerns promptly. Next up, if you like what we're doing on the YouTube channel, please subscribe to the Data Science Dojo YouTube channel. We will be producing new content weekly, so if you subscribe, you'll keep abreast of all the latest and greatest things that we're doing. Also, more generally, if you like what we're doing at Data Science Dojo, hook up with us on social media. We're on Twitter, Facebook, LinkedIn, YouTube, you name it. Hook up with us and you can get a nice, steady stream of data science goodness sent your way. And I hope to see you, lastly, in one of our upcoming data science boot camps. So until next time, this is Dave Langer, and I'm wishing you very happy data sleuthing.